Massive MIMO beamforming uses a large number of transmitting antennas to send focused beams toward individual users. And this allows a base station to send simultaneous data streams to many users within the same small cell, within the same frequency band at the same time. To do this, the base station receives pilot signals from each of the devices in the scene and uses those to characterize the channel between the base station and the devices. It then sends different signals to different users over the same frequency by forming individual beams to each of the users. This shared frequency increases the capacity and the data rate overall. On the bottom left, we show a diagram of how this kind of beamforming is often conceptualized. So the base station with its large array of antennas can form very narrow beams to individual devices. But the reality is that in an urban small cell, with all of the multipath and reflections and diffractions off of buildings, there may be a much more complex beam. And on the bottom right, we show an example of beamforming from 128 transmitting elements from a base station shown in green to a device shown in red. And this is using a technique that also tries to minimize interference to these other devices shown as red circles. We can see that in this case the beams are bouncing off of buildings, and there are actually multiple beams being sent in and around and through the multipath. So clearly beamforming can be quite complex compared to a simple narrow beam diagram. To simulate MIMO, one technique is to use three-dimensional ray tracing. In wireless InSite, this is the technique we use. 3D ray tracing provides a great deal of information about multipath. If we look to the diagram to the right, we can see individual paths, some of the strongest paths between a transmitter and a receiver moving along a route. These paths then translate into what's called the complex impulse response, shown at the bottom right, which shows the arrival of copies of the signal as a function of time. So 3D ray tracing can capture this level of detail. It can provide the complex path gain, sometimes known as the complex channel matrix. It can provide detailed 3D path data with all of this information about the time and also the phase information between all of the elements of the antennas at the transmitter and the receiver, the angles of arrival, the polarization, and all the other details that are critical to understanding the multipath in the scene. And perhaps most importantly, a solution that uses ray tracing can ensure that as something moves through a scene, you get spatial consistency from point to point, something that a statistical technique would not be able to capture. The fact that the paths may not change very much over a local area, but then can change dramatically over the full course of a route.